It's my pleasure today, my great honor to introduce to you to Michael Pradel, a leading researcher in software engineering whose work has significantly advanced the state-of-the-art in program analysis, software testing, and machine learning-based software engineering. I hope this covers most of, can I put in the word guarantee in there somewhere, and then we have covered everyone? Michael is widely recognized for combining deep technical rigor with practical relevance, producing methods that both shape academic discourse and influence real-world software development. His career spanned stations such as ETH Zurich, Berkeley, TU Darmstadt, University of Stuttgart, Facebook, UCLA, and now CISPA. He is a distinguished ACM member. He got the Ernst Tenured Award for the best PhD thesis in software engineering. He has 2 ERC grants, Consolidator and Proof of Concept, an Emmy Noether stipend, and the list goes on and on. Fittingly, though, Michael is also an avid runner, something that reflects his research style remarkably well. Sustained focus, discipline, and the ability to tackle long, challenging problems without ever losing sight of the finish line. Actually, never even accepting there would be a finish line. Beyond his research, he's a dedicated mentor, a super friendly guy, and an active contributor to his community and the mission of CISPA. We're very glad to have him with us, to have him here today. Please join me in welcoming Michael Pradel.
All right, yeah. Can you hear me, actually? Yep. Okay. Yeah, thanks a lot for this very kind introduction. It's going to be very hard to live up to that, but I'll try. Yeah, it's really a great honor to not only give this inaugural lecture, but actually give the inaugural lecture, because this is the first inaugural lecture at CISPA, so there's some meta level to that. So yeah, thank you all for coming. What I want to do in this 1 hour that we have here, or a little less now, is to see what the marathon and intelligent software tools have in common. And the very short answer to that question is, well, me, because as Andreas already said, I am actually a pretty avid runner. I really like to run, and also have been stupid enough to run a couple of marathons. But I'm also working on these intelligent software tools, which are basically techniques to help developers do their job in producing good software. And I'll talk more about this in the next 1 hour. Before doing this, let me just tell you a little bit about how I came to be here. So once upon a time, there was this cute little guy, which happened to be me, who was born in Jena. And then at some point, I decided I should go studying. I was a little older by then, and started my undergrad studies in Dresden, at TU Dresden, where I started to study computer science. And then at some point during an operating system lecture, the professor Hermann Hertig said, oh, there's this nice opportunity to go to Paris for 2 years. So you can get 2 degrees and spend 2 years in Paris. And I thought about it, and yeah, okay. I mean, I had stopped learning French after 10th class and thought I would never need it again, so why not? Let's go to Paris. So I spent 2 wonderful years in Paris, and then got 2 degrees in computer science and in also engineering. But the engineering part means I should, in principle, be able to build nice monuments like this. But yeah, I have never tried, so I'm not sure if that's actually true. Yeah, and then for my master thesis, I also wanted to go to yet another place. And another professor of mine, Uwe Assmann, suggested that I could do this at EPFL in Lausanne, where I joined the Scala team around Martin Odersky and spent 6 wonderful months contributing to Scala a little bit. And I learned a lot about programming languages, language design, compilers, and similar topics. And as you can see, I really enjoyed being in Switzerland because there are nice mountains and you can do also interesting things beyond research. So I decided to stay there and ended up doing my PhD at ETH Zurich, where in 2012 I defended my thesis on this title, which is actually not so different from many of the things that I'm still working on today. And as you can see, I'm strategically circling around Saarbrücken, and you might think that the next step obviously leads me to CISPA, but that's not true. Oh, sorry. That's the disadvantage of not seeing the next slide. So there's a little quiz to make sure you all are awake, which is this picture taken at the PhD ceremony of ETH Zurich. And the question is, where is Waldo? Where is Michael? Can anyone spot me? What, left of program? Yes, exactly, left of program. This guy here. As you can see, I was the only one who was not wearing a suit. Somehow I didn't get the memo, but they still gave me a PhD, so everything was fine. Anyways, then after that, instead of directly coming to CISPA, which would have been nice, but I think back then it was non-existent or maybe very small, I'm not sure. I went to sunny California to do a postdoc at UC Berkeley, where we spent a wonderful year as a family also, and then came back to good old Germany and became an assistant professor at TU Darmstadt. And now you might think, now it's time to go to CISPA, but actually no. I decided I should go one more time to sunny California. And given the fact that I work so much on tools and techniques for software developers, I thought maybe it's a good idea to actually see how they work in practice. And I did this by spending 6 months during a sabbatical at Facebook, where back then they were really doing state-of-the-art work in applying machine learning in software development, so that was a pretty good fit. And from there, my path eventually led back to Germany when I became a full professor at the University of Stuttgart, and eventually also became tenured faculty at CISPA, which is why I'm here today. Good, so now you know a little bit more about me. Let's now talk a bit about the work that me and my team are doing. And the overarching mission that I've been pursuing for quite a while now is centered around this question. So how to enable software developers to create software that is reliable, secure, and efficient. So basically 3 qualities that you ideally want to have for every piece of software. And now, of course, there are many different answers you can give to that question. The one that I'm most excited about is to give developers the right tools, because once you have the right tools, you can typically do really good work. And specifically, we've been working on neurosymbolic reasoning tools that analyze and repair code while connecting fuzzy human intent and precise program behavior. That's a pretty long statement, I know. So let me break it down into smaller pieces. So there's this neurosymbolic part, which basically means that we are very often combining techniques from machine learning, in particular neural networks, with more symbolic algorithmic reasoning techniques that reason about programs using a more mathematical and symbolic foundation. We do this to analyze and repair code, where analyzing code, for example, means that we point out errors, bugs in a program, and repair code means that we have automated techniques to fix those bugs. And finally, with this last part, connecting fuzzy human intent and precise program behavior, what I mean is that there usually is some idea of what a piece of software is supposed to do. So there's some intent that a human somehow can express, but it's usually a bit fuzzy because it's not formally specified and you can't fully capture it, at least not in a mathematical way. And connecting this with the actual program behavior, which is very precise, is a big challenge. And this is part of the challenge that we are addressing. And now, to make all of this a bit more fun, I want to convince you along this presentation that all of this is a bit like a marathon, because it is really a long-term effort. And I'll show you a couple of other parallels between what we are doing in our research and running marathons. Good. Before telling you how we do this, let me quickly tell you why this actually matters. So the main underlying reason of why I do all this work is because software is practically everywhere. Here are a couple of interesting statistics about how many billion smartphones there are in active use globally, and the fact that most office works involves software, and that almost all financial transactions that are done are digitally processed, so based on software. If you take any means of transportation, let it be a car or a modern plane or a train, there will be millions of lines of code that are basically in this vehicle, and all of this is a big part of the industry. And just to give you one number from a study I found, the software industry contributes 1 trillion euros per year to the EU economy. So it's a huge contribution. And that, of course, means that software needs to be reliable, secure, and efficient, because if it doesn't work, many things won't really work well. So today in this talk, we're using Zoom, I think, to also have a few people join this online. And of course, we rely on the fact that Zoom is working. So if, now we would get this, it would be very unfortunate, right? So this is just one example of what we do not want to have. So we really want the software to work. Now, in order to avoid failures like this. Let's maybe see if we can learn from failures done in a completely different domain, which is, in this case, running or hiking, actually. So when I was 21, so about, well, pretty much exactly half the age I'm now. Now you have a timestamp. A good friend of mine asked me about this event which was happening, which was a 100-kilometer hike. And he said, hey, you want to try? We can do this together. And I was like, yeah, why not? I mean, I had been hiking. I had, of course, never been hiking that far, but I was naive and said, sure, let's do it. What I had not realized is that if you want to hike for 100 kilometers, you basically take 20 to 24 hours. So you typically start in the evening, which means the first 12 hours you're hiking in the dark. So I still remember us basically going through the forest with 2 torchlights and not seeing anything. So it wasn't really a beautiful hike, but it was just darkness and the 5 meters ahead of you. And guess what? Because we weren't really prepared at all. After 60 kilometers, we were completely devastated and dropped out. So that's clearly a failure. The question is what does that have in common with software? Well, a marathon or hiking a very, very long distance and intelligent software tools have that fact in common that success is decided in the long run and not on race day. And what that means for hiking and running is that you need to train, you need to practice, right? And you can't just go to such an event and hope for the best, which was what I did. And what that means for software is that the success of a piece of software is decided during software development. So we really need to make sure that during software development, we are equipping developers with the right tools. Now, to do this, let's again look at this analogy between running and software. And first think about what is required in order to train effectively for a larger run, like this 100K hike or maybe a marathon. And typically, training in running involves 3 steps. You plan your run, so you think about what you want to do, what kind of run you want to do. Then you actually run, and then your body is probably a little bit broken, and you need to recover it. And in software, it's actually very similar because you also have 3 phases that are sort of related to the 3 phases that I just laid out for running. The first one is that you write the code, which basically means you're writing down a plan for what should happen when the program is actually executing. And then you run the program. That's very clearly like running. And finally, recovering from failures or from injuries or just from fatigue is very similar to fixing bugs because you want to fix what is broken and patch up the software or the runner. And I'm arguing that for all of these 3 steps, it's very important to have these intelligent tools that help software developers to do these steps right and to find and prevent mistakes in particular. So let me give you a few examples of tools and techniques we have developed that fit into these 3 steps of software development. And I'll start with the first one, which is about the planning of your run or the writing process of a piece of software. First, let's again look at running. And let's assume you now start running. You're very motivated. You have realized that you should train. And you have a good friend who's an even more avid runner, and you ask him or her for some advice on the next run. And then your friend answers and says, you should take it easy today. You should go 7 kilometers at a 3 minute per kilometer pace. Sounds like solid advice, right? I mean, can anyone spot anything that's wrong? Huh? Speed, okay. I see some people are into running. Yes, exactly. I mean, if you are able to run 7 kilometers at 3 minutes per kilometer, it's possible, but you're probably world elite, right? You're one of the top 100 runners or so on this planet, which is, at least not the case for me. So this would not be good advice for me. But what's interesting here is that if you just look at the language, English in this case, this statement makes sense, right? It's grammatically correct, and if you do not know the domain and what the friend in this case wants to express very well, you might think this is correct and everything is good. And interestingly, very similar problems arise in source code, where you also have code that may be correct according to the specification of the language and may make some sense if you look at it just in a cursory way. But if you look more deeply at the actual semantics that the programmer wants to express, you'll see that things are wrong. This is one of my favorite examples because it's just 4 lines of code It's in a language that probably not everybody knows. It's JavaScript, but probably many people in the room don't really know it. But still, many people usually look at this, and if they look a little bit longer, they see what is wrong. Anyone sees what's wrong? Right, exactly. So the x and y arguments that we pass to this setPoint function are clearly in an incorrect order. But interestingly, similar to the example that I just showed you in English, this is something that you can only understand if you understand what the intent of this code is. You somehow get from the variable names what this code wants to do, and then you realize that this is wrong. But if you just look at the language, these are two variables, they have the same type, you pass them to this function that expects integers apparently, so everything looks good. But still, you need to understand the intent in order to see that this is wrong. Now, interestingly, traditional program analysis techniques are really bad at spotting this kind of problem because they don't reason about these fuzzy things like identifier names, and yeah, therefore they cannot really find this problem. So in one of our, by now I would say earlier pieces of work, because it's already 8 years or so, called Deep Bugs, we try to address this kind of problem by basically learning to find bugs. And the key idea back then was to train a model that distinguishes correct from buggy code. So essentially what you need to do this is two sets of code, some examples of buggy code and some examples of correct code. And then given these two sets, you can train a machine learning model that serves as a classifier and that given a new piece of code can classify whether this piece of code is correct or buggy. And there are many ways how you can instantiate this overall pattern. We've instantiated it in different ways, which among many other examples find the bug that I've just shown you. And yeah, this was also adopted by a couple of practitioners, a team at Google and also a team at JetBrains. So I think it turned out to be a pretty good idea actually. All right, now this was about finding mistakes. Now let's get back to the running analogy. And let's assume that after a little bit of training, you decide you want to add some structure. So initially, your training basically looked like this. You just said, hey, let's just run. I feel like today is a good day for running. Let's just go out and run. But then in order to get faster and stronger, you at some point realize that you want to have a more structured training plan. So you want to come up with something like this that tells you on what days to run, on what days to rest, how fast to run, and so on, right? And in software, you actually have a very similar situation, in particular when you're dealing with dynamically typed languages like Python or JavaScript, where over the evolution of a project, at least if the project is successful, people at some point realize that you also want to add structure. So initially, there typically is a small code base with just a little bit of code here and there, and everything is under control. But then if the project is actually successful, the code base is going to grow. And in a dynamically typed language like Python or JavaScript, these large code bases tend to be very hard to maintain. And one of the reasons is that there is a lack of structure, in particular because there are no type annotations. So you basically don't really know how these different pieces of code fit together. You just execute them together and somehow hope for the best. But there's no way of checking that they fit together before you execute the code. So what people want to do is to actually turn the code base into something that looks a little bit more like this, where the code now is well structured because you have type annotations that make sure that the different pieces that are supposed to fit together actually do fit together. Now, I've written ideally on this arrow because in practice, this is not a task that software developers like to do. You basically have to go back to an old code base, understand what it's doing, and then add all these type annotations just to basically make it do the same. And with this long-term goal of making it more maintainable, it's not very, very motivating. And this was also the situation that Facebook was facing back then when I was doing the sabbatical. And they had a lot of Python code in their code base, but they didn't have type annotations. Now, fortunately, we had come up with an idea just a couple of months before that in my lab, and then introduced that in Facebook, which they are called typewriter. And that idea was to use a neural network to predict the types that you should add to your code. So what we do here is to take all the information we can find about the software, including the code itself, but also more fuzzy information like identifiers or comments, and then train a neural model that predicts the missing type annotations. And if you do this naively, you will get some type annotations that are wrong, simply because neural models are never really perfect. But the good news is that there is a symbolic tool called a type checker that can make sure that type annotations you add to a project are actually consistent with each other. And by combining these two techniques in a clever way, we can basically get a tool that can, at the end of the day, guarantee that you add only correct type annotations to your code base. All right, so again, let's get back to the big question. What do a marathon and intelligent software tools have in common? And one other commonality that I've just illustrated is that you must identify mistakes and enforce some structure in order to support growth. That's true both for running and also for software. Good, now let's move on with our training. And let's now say we have done enough planning, so we have spent enough time on writing the code and reasoning about the code, and now what we want to do is we want to actually run the code. Now, as a runner, at some point, you are very interested in how exactly you perform, and you start monitoring your runs. So you want to get statistics like this, where you see your pace over a particular run, your heart rate maybe, and your stride length, and many, many other interesting statistics. And by doing this, you can get some feedback on your running and then improve your training. How do you do this? Well, for running, it's actually fairly easy. You take the runner, you take a watch, you put it on the wrist, and then magically you get all these statistics. It's very easy for running, and it would be really nice if you could do the same for software, wouldn't it? For software, you can also do something like this, where you take your software, you take something called a dynamic analysis. So for those who are not really deep in computer science, think of this as a runner's watch for software. And you put it on the wrist, which in this case is called instrumentation, and then you execute these two jointly and can get a lot of interesting runtime information about the software, and you can use this to find bugs, find security problems, and improve your software. Now, the tricky part is this instrumentation, because what it means is that you look at the source code of your software, and then you want to modify this original source code at a very fine-grained level, and doing this correctly and maybe also efficiently, if possible, is actually pretty tricky. And now the naive approach would be to just do this over and over again each time you want to do some monitoring of your software. What you can do instead, and this is something we've been also working on, is to develop dynamic analysis frameworks. So these are basically tools that allow you to relatively easily write a dynamic analysis, so one of these monitors, in order to look at the behavior of the program. So I'll just give you a glimpse into how this works. So you start with your original source code, for example, a Python file or multiple Python files, and then have this instrumenter which is adding additional instructions into the source code, which then call a component called the runtime engine. And what this runtime engine does is to look for events that are relevant for your dynamic analysis, so kind of the statistics you want to monitor or the runtime events that you care about. And if they happen, it calls into the analysis, which can also take a look at the original code and some other metadata. And the key takeaway is that this makes it relatively easy to implement these dynamic analyses, and you don't have to basically instrument all the source code by hand, but this is done automatically. Now, what can you do with all this nice monitoring? You can actually use it to achieve the three goals that I laid out initially: reliability, security, and efficiency. So, for example, we've worked on this concept called dynamic linting, which is a little bit like linting of source code, which means you statically scan the source code for particular anti-patterns. But you can also do this at runtime now, where you at runtime look for specific patterns of things that should not happen. And if you see these patterns, you report a warning to the developer, who can then fix the program. You can also use it for looking into different kinds of security properties. For example, you can perform dynamic taint analysis to find the SQL injections, or you can observe the behavior of the program and look for particular patterns in the computation to check if an obfuscated piece of JavaScript is, for example, a crypto miner. And finally, we've also shown that you can use this for improving efficiency, for example, by detecting specific memory leaks in machine learning code, which, if not detected, would probably lead to an out-of-memory error of your machine learning pipeline, which is something you, of course, want to avoid. All right, so getting back to the big question, as you have seen now, there's yet another commonality between running a marathon and intelligent software tools, which is that you need real-world feedback from actual runs and not just theoretical reasoning in order to be successful. Cool. Now let's also look at the third part of this bigger picture, which is about recovering after a run or actually fixing bugs in your code. I guess for a run, it's pretty obvious why you want to do this. If you've done a tough run, you're really tired and you need time to recover and get patched up. For software, you have a very similar situation. And this is because most software has many bugs. So the software also needs to get patched up. So this is an example from Minecraft, which is a piece of software my kids like a lot. So I added this slide just for them. And they are very embarrassed now, of course. Which shows a bug in Minecraft which happens after some TNT is exploding, but it doesn't have the effect that apparently you want to have in this game. And as you can see from these numbers, this is not just one bug, but this is one out of more than 300,000 that have been reported in Minecraft. And this is not a very unusual situation because most successful and complex software actually has thousands of unresolved bugs that the developers just have not yet had time to fix. So what you want is some automated way of fixing this bug. And this is a research field called automated program repair that I've also contributed to. Let me give you two examples of how to automatically fix bugs in software. And the first one was inspired by this idea that we could actually look at how humans fix a particular kind of bug and then learn from these human bug fixes in order to apply similar fixes to other source code locations. So this was, again, work done during the sabbatical at Facebook in a tool called Getafix, which back then was the first industrially deployed automated program repair tool that learns from past human-written fixes. So here's an example that shows how this works. So what you see on the left is a warning reported by a static analysis that in this case says that there's some potential null dereference. So for those who are not programmers, a null dereference is bad. It basically means your program is crashing. And instead of just telling the developer, hey, your code is wrong, what Getafix now is doing is to also suggest a specific fix. And all the developer has to basically do is look at this suggested change, which says, hey, remove this one line and instead add this other line. And if this looks good to you, you just need to click accept, and then you immediately have applied this patch. So this worked pretty well and helped solve thousands of bugs in practice. I'll tell you on one slide, or try to tell you on one slide, how this works. So the basic idea is that we have all these human edits that were made in the past in order to fix similar kinds of bugs. And we try to mine from these edits recurring edit patterns that we can then apply in other places. So each of these blue boxes is one human edit that was made by a human developer at some point. For example, these A and B edits could be the two edits that you see here, where the code on the left of the arrow is transformed into the code on the right of the arrow. And then what Getafix is doing is it tries to find commonalities between these human edits and tries to abstract them a little bit so that they are basically becoming the same. So in this case, we would basically combine A and B into AB, where we now abstract away the specific identifier names that are used here into these holes, H0, H1. And then you can suddenly see that these two edits A and B are the same. And now you can do this again and again until you have constructed this hierarchy of edit patterns where at the top you have a very generic replace some piece of code to some other piece of code. And at the bottom you have these very specific edits as they were made in the past. And somewhere in the middle you have patterns that are applicable in other code locations and that can be actually used to suggest fixes. All right, so this is what we did a couple of years ago. And then more recently, we were wondering what would happen if you would not just learn from edits that people have done in the past, but let artificial intelligence basically take the steering wheel. And we implemented this idea in a technique called repair agent, which was the first LLM-based agent for automated program repair. And the way these agents generally work is that you have a large language model which interact with a set of tools and can basically autonomously decide how to use these tools. So for the task of automated program repair, you provide a bug that you would like to fix to the LLM, and then the LLM can use different tools that are very similar to what a human developer would also use. For example, tools to read and extract code, or tools to search and generate code, or to modify code, or to run some tests. So similar to what human software developers are using. And the LLM is telling us how to use these tools, or basically uses the tools, until it finds a patch that actually fixes the bug. And yeah, this turns out to work pretty well, because LLMs are really powerful, and also because we found a good way of connecting these two techniques with each other. Let me see. Yeah, okay, I'll tell you a bit about the technique. So going back to this, so if you just give all these tools at once to an LLM, what typically happens is that it gets a bit confused and sometimes takes very suboptimal decisions. For example, one suboptimal decision might be to just immediately modify the code. So without really knowing what's going on and what the problem is, the LLM thinks, oh, let's fix it. But it doesn't really know how to do it, so it's just guessing. Or another not so clever way of using these tools would be to just read more code, read more code, read more code. So you never go to the stage where you actually start fixing the code. And in order to prevent this, what we do in Repair Agent is to guide the usage of these tools by specifying this finite state machine, which guides the agent through the typical phases of fixing a bug by saying that you first need to understand the bug, where you can, for example, read code. Then you need to collect information to fix the bug, where you can maybe search for other pieces of code that are similar. And then at some point, you want to start actually writing a fix. And this is when you go to the third state. And finally, if you manage to pass all the tests, then you are in the done state. And by providing this structure and limiting which tools to use when, the agent is much more effective in actually repairing software. Okay, so again, what do marathon and intelligent software tools have in common? Well, failure is part of the game. And what matters is how well you recover. So that's true for running, obviously, but it's also true for software, where the software is never really going to be perfect, but you need to have good ways of handling and preventing and fixing bugs. All right, now you might say, if you have all these bugs, wouldn't it be better to catch them sort of on the fly before they are landing in my software? And the analogy to running would be if you wake up in the morning, you put on your shoes, and it somehow looks like this, should you really go for the run and wait until you fail because you've put your shoes on in the wrong way? Probably you should not, right? So the question is, can't we somehow prevent bugs from even being introduced into the code base by finding them much earlier? And this is something we've been working on in one of our most recent techniques called Testora, where the basic idea is that we are cross-checking the human intent as expressed in natural language that describes a code change with the behavioral change that we see in the software. So let me illustrate this with one example from the SciPy project, a Python library for scientific computing, where you have this pull request that describes that the way this library internally handles different array types should be changed, while at the same time the publicly visible behavior of this library should not change. So basically, from a user's perspective, despite this change, nothing should change. And now what Testora does is to try to find examples that contradict this intended behavior of the change. And in this case, it found an example where you're basically using this library by calling the function that was modified in the pull request. And when you execute this, you'll see different behavior before the pull request, so in the old code, and after the pull request, so in the new code. And in this case, this is clearly unintended, and this is what people call an unintended regression. And Testora finds these automatically. So by doing this, it can basically try to prevent some of the bugs from landing in your code base, so that they never even make it to users. Good. So so another commonality between a marathon and intelligent software tools is that problems are cheapest to fix when caught early, and Testora is one way of achieving this. So now, we've gone through our 3 steps of training, and I've shown you different examples of our work that fit into these 3 parts. And now we can go to the race and run and be happy and say, hey, we're done. But I could also tell you a little bit about what's next. So basically, what's the future work? So after we've run this one race, what do we want to do? What do we want to do next? The obvious elephant in the room is, of course, that we are entering or have entered already this AI era, right? So artificial intelligence is getting so strong that it definitely has an impact on many domains, but in particular also on software development. So I think one of the key questions we should all ask ourselves is, how does software development look like in 5 or maybe 10 or maybe even more years from now? And one way to answer that question, which is very pessimistic and not the one that I want to give, is that AI is basically taking over. It's doing all the software development. People who used to be paid a lot of money because they can write code are pushed out of their jobs and have to do something else. I think this is not what's going to happen. I think my more optimistic take on this is that we will have a future in which AI software development assistants and humans actually collaborate, so that the AI assistants are working on the more mundane and maybe boring tasks, and the more creative and interesting tasks are still being done by the human developers. Now, it's actually not bad that this is hopefully at least happening, because it's actually a good time to delegate some of the work that we see in software. And the reason is the following. So if you look at how things are evolving over time, so right now we are here, and you look at how many software developers there are worldwide, then this is more or less constant. It may increase a bit, it may decrease a bit, but it's more or less constant. At the same time, if you look at the number of software packages that we have, no matter in what software ecosystem you're looking at, you will see a pretty steep increase, sometimes an exponential increase, of the number of different software packages. So who's maintaining and evolving all of this software? The software developers probably are not, because they are not as many as we would need. So what this means is that there will be more and more a large portion of the entire software ecosystem that is very purely maintained. And actually, we are already seeing this a bit right now, because there are a lot of packages that are full of bugs, full of vulnerabilities, and there's not really enough human time to take care of this. So the vision where I hope we are moving to is that with AI assistants, we can have some of the software packages that exist in the software ecosystem. We can turn them into self-evolving software, which basically means that the projects are not really dependent on human development time so much, but they are evolving more or less on their own, maybe with a little bit of human input here and there, but the humans don't have to take care of those packages. And of course, at the same time, there will be some that are still fully human evolved, but definitely not all of them. In analogy with self-driving cars, I think you can map this into different levels of self-evolution, where until a couple of years ago, we basically were here in software development. Everything was done manual. There were some tools, of course, but not a very, very strong assistance. Then level 2 is what we are basically at today, where you have some AI assistant, but the main person at the steering wheel is still the human. And where I would like to go in the future is level 3 and level 4, where in level 3 we can have self-evolution at the project level. So individual projects can basically be turned into self-evolution mode and don't really need much human assistance anymore. And level 4 means that we can do this even at a larger ecosystem scale by having entire sets of packages, or maybe complete domains in which you have software be in this self-evolution mode. Now, doing this, of course, is far from trivial, and there are a lot of very interesting research challenges on the way. And I think they can be grouped into these 2 big categories. The first one is complexity. So how do we automate very complex multi-step maintenance and evolution tasks? We currently don't really have a good answer. So AI is able to help us with tiny code examples. It has proven that it can do this, but how to scale this to entire projects or even multiple projects, it's not fully clear. And the second question is about how to scale the self-evolution to the ecosystem level, so not just individual packages, but have multiple packages that co-evolve together and do this without needing a lot of human assistance. And then the second set of challenges is around trust, where the big question is how to establish trust into AI-generated code. Right now, it's very easy to generate a lot of code with LLMs, but not all of this code is correct. There are vulnerabilities, there are tons of bugs, and many things that you actually would not want to have in your software project. And we need better techniques to establish trust into this AI-generated code. And also, we want to align the AI-based software engineering with human needs and values so that self-evolution actually moves into the right direction that matches those needs and values that humans have, instead of turning packages into self-maintained but basically dysfunctional pieces of software. All right, so after this short look into the future, let me get back to my big question of the lecture. So what a marathon and intelligent software tools have in common. Success is decided in the long run, not on race day. So we need to take care of training/development. We must identify mistakes and enforce structure to support growth. You need real-world feedback from actual runs, not just theoretical reasoning. Failure is part of the game. What matters is how well you recover or how well you fix your bugs. And finally, problems are cheapest to fix when caught early. So before opening the floor to questions, let me use the opportunity to thank a few people. First of all, my family, who is also in the room and who is also crazy enough to go running. But also has been crazy enough to move around with me, and we've been in California together a couple of times, and they are also very tolerant when I'm hiding in my office because there's yet another deadline or I'm going to yet another conference, so thank you very much for that. I would also like to thank my amazing team of PhD students, most of which are also in the room here today. So without such a strong team, of course, we would not be able to do all of this work. And this includes, of course, students who are not in the group anymore right now, but have graduated at some point. So they are not here, but I still want to mention them. And then finally, I would, of course, also like to thank people at CISPA. So I've just started here in September, and from the beginning felt very welcome because all the faculty members have been very welcoming and did a great job in showing me around. There are many names I could mention. I just want to point out 3 people. I know that at least 2 of them are in the room. One of them is Miriam, who was my point of contact in faculty onboarding and did a really great job in introducing me everywhere and telling me all the little tricks that you need in order to survive in any bigger organization. And then, of course, also Anja and Sally, who are in the room and who are taking care of a lot of organizational and administrative tasks, which is amazing because otherwise we wouldn't have time to do all of this research work. So thank you very much for that. And with this, I'm at the end of my talk and would be happy to have some questions. Thank you.